Hello everyone, this is your Professor Rami and I am here with my teammates to explain you the timeline key milestones of atomic models and their creator. From 12C,
Professor Dave explains.
Atomic Timeline. In here, we're going to discuss the timeline of the different atomic models and their creator. Ancient Greece, Sisyphus and Democritus proposed the idea of the atom, 5th century BCE. Sisyphus and Democritus were early Greek philosophers who, in the 5th century BCE, proposed the idea that all matter is composed of small, indivisible units called atomos, or what we call atoms. Their atomic theory suggested that these atoms are eternal, indestructible, and move through the void, combining to form different substances. This concept laid the foundation for later atomic theory and was a significant departure from earlier ideas that viewed matters as continuous. Although their ideas were largely speculative, they were crucial in the development of later scientific thought on the nature of matter. Number 1. Historical context. In time period, Sisyphus and Democritus lived during the 5th century BCE, a period of intellectual flourishing in ancient Greece. This era saw the rise of pre-Socratic philosophers who were interested in explaining natural phenomena beyond mythology and religion. In philosophical environment, they were part of the Ionian school of thought, which emphasized naturalistic explanation of the universe. Philosophers like Heraclitus and Anaxagoras also explored the nature of matter, but their ideas differed from those of Sisyphus and Democritus in significant ways. Number 2. Sisyphus. His role. Sisyphus is traditionally considered the founder of atomism. Unfortunately, little is known about his life, and some scholars even question whether he actually existed as a distinct person or if he was simply a character associated with Democritus' work. His ideas? Sisyphus formulated the basic premise that all matter is composed of small, indivisible units, atoms, moving in a void. This idea represented a major departure from the earlier Eleatic school. Example is the Parmenides that denied the possibility of empty space. Number 3. Democritus, student and elaborator. Democritus, a student of Sisyphus, further developed and popularized the atomic theory. He is often credited as the primary figure in ancient Greek atomism. His core ideas, starting from number 1, atoms and void. Democritus asserted that all matter is made up of tiny, indestructible, and indivisible particles called atoms, from the Greek word atomos, meaning uncuttable. Second, qualities of atoms. Atoms, according to Democritus, differed in shape, size, and arrangement, and these differences accounted for the variety of substances in the world. For instance, the sharpness of atoms was thought to contribute to the bitterness of certain substances. Third, movement and combination. Atoms were believed to move in the void and combine to create the object we perceive. Changes in the world were explained through the rearrangement and movement of atoms. Fourth, mechanistic worldview. Democritus had a mechanistic view of the universe, believing that all phenomena could be explained by the interactions of atoms in space, without invoking any purpose or divine intervention. Number 4. Philosophical significance. In materialism, Democritus' ideas laid the foundation for materialism, the philosophical stance that all reality can be explained by material interaction. He also argued that human perception and emotions were the result of atomic arrangement within the body. In determinism, Democritus' philosophy was also deterministic, suggesting that everything that happens is determined by prior atomic interactions without randomness or external purpose. In ethical ideas, Democritus held ethical beliefs that emphasized happiness, like eudaimonia, which he argued came from leading a life of modern and rationality. He advocated for self-control and knowledge as path to achieving tranquility. 5. Impact and legacy. Limited influence in antiquity. During their time, the atomist theory was not widely accepted. Competing theories from philosophers like Plato and Aristotle, who believed in the continuity of matter and rejected the void, overshadowed their ideas. Aristotle's concept of the four elements, earth, water, air, fire, dominated Western thinking for centuries. Revival in the modern era. Atomism re-emerged during the scientific revolution in the 17th century, influencing scientists like Galileo, Newton, and especially Dalton in the 19th century, whose atomic theory formed the basis of modern chemistry. Philosophical echoes. The concept of atoms and the void influenced the development of Epicureanism, a school of thought founded by Epicurus, who adopted atomism and integrated it into his teachings on ethics and the pursuit of pleasure. 6. Conceptual contribution to science. The speculative nature. It is important to note that Lucifer's and Democritus' ideas were purely philosophical and speculative. They lacked experimental evidence but contributed significantly to the tradition of questioning and theorizing about the nature of reality. The early scientific thought. Their focus on natural explanations, mechanisms, and reductionism, the breaking things down into simpler components, is echoed in modern scientific approaches to studying nature. In summary, Lucifer and Democritus laid the intellectual groundwork for the concept of the atom, which, although not scientifically rigorous by modern standards, represented an early attempt to explain the material universe through a fundamental, systematic principle. Their work was largely speculative but was foundational in moving away from supernatural explanations of natural phenomena. Their ideas on atoms and the void resurfaced much later and provided inspiration for scientists who shaped our current understanding of matter.
Stop, Professor Dave explains.
John Dalton formulates the first modern atomic theory 1803. John Dalton was an English chemist, physicist, and meteorologist who is best known for formulating the first modern atomic theory in 1803. His work was foundational for modern chemistry and marked a turning point in the understanding of matter. Historical context, scientific background. By the late 18th century, the concept of atoms as proposed by ancient Greek philosophers like Democritus had largely faded from scientific discourse. Instead, the dominant theories of matter involve continuous elements and various chemical substances. Chemistry development. The late 18th century saw significant advances in the study of chemical reaction, gases, and elements. Unlearned laboratories work on the conservation of mass and the identification of elements paved the way for a systematic approach to chemical study. John Dalton's life and early work. Early life. In the year 1766 to 1844, John Dalton was born in Eaglesfield, England, to a Quaker family. He started teaching at a young age and was largely self-taught. He became known for his contribution to a variety of scientific fields, including meteorology. Interest in gases and meteorology. Dalton's interest in the behavior of gases led to important observation about atmospheric pressure and the properties of gases. His research on gases would ultimately lead him to consider the composition of matter on a fundamental level. Development of atomic theory. Dalton studies on gases. Dalton was interested in studying the properties of gases and how they interact. His investigation led him to consider how gases mix and why the ratios of different gases were consistent. He began to think about the underlying particles that made up these gases. Law of Multiple Proportions, 1803. Dalton observed that when two elements combine to form multiple compounds, the ratios of the masses of one element that combine with a fixed mass of the other element are always in small whole number ratios. This principle is known as the law of multiple proportions and was critical in shaping his atomic theory. Key postulates of Dalton's atomic theory, 1803. Atoms as fundamental particles. All matter is made up of small indivisible particles called atoms. Atoms are the fundamental building blocks of matter and cannot be created or destroyed. Atoms of the same element are identical. Atoms of a given element are identical in size, mass, and other properties. This means that all atoms of an element behave in the same way during chemical reactions. Atoms of different elements differ. Atoms of different elements have different properties such as varying weights and chemical behaviors. Atoms combine in fixed ratios. Compounds are formed when atoms of different elements combine in simple, whole number ratios. This explains why chemical reactions occur in fixed proportions and how the same elements can form different compounds. Chemical reactions involve rearrangement of atoms. Chemical reactions involve the rearrangement of atoms to form new substances, but atoms themselves are not created or destroyed during chemical reactions. Dalton's atomic weights and chemical symbols. Atomic weights. Dalton also introduced the concept of atomic weights. He attempted to assign relative weights to atoms based on their observed behavior in chemical reactions. Although his values were not always accurate, they represented an important early attempt to quantify atomic masses. Chemical symbols. Dalton used a system of symbols to represent elements in his chemical formulas. These symbols were less refined than the current system, but they were a precursor to the standardized chemical notation we use today. Impact and significance. Establishing the atom as a scientific concept. Dalton's atomic theory marked the beginning of a modern understanding of chemistry. By providing a scientific basis for the existence of atoms, Dalton transformed atomism from a philosophical concept into a scientific one, which could be tested and used to explain chemical reactions. Explaining conservation laws. Dalton's theory helped to explain the law of conservation of mass and the law of definite proportions. These conservation laws could be understood in terms of atoms combining in fixed ratios without any loss or creations of matter. Foundation for modern chemistry. Dalton's atomic theory served as a foundational basis for later development in chemistry, including the periodic table by Dmitri Mendeleev, the concept of moles, and Avogadro's law. It laid the groundwork for understanding chemical bonding, atomic structure, and molecular interactions. Limitations of Dalton's theory. Indivisibility of atoms. Dalton believed that atoms were indivisible. However, the later discovery of subatomic particles, protons, neutrons, and electrons in the late 19th and early 20th century showed that atoms are made up of smaller components. Isotopes not accounted for. Dalton's idea that all atoms of an element are identical was later found to be incorrect with the discovery of isotopes. Atoms of the same element with different masses due to varying numbers of neutrons. Inaccurate atomic masses. While Dalton made efforts to determine atomic masses, the technology of his time was not sophisticated enough and his values were often imprecise. Dalton's other contributions to science. Meteorology. Dalton made significant contributions to meteorology, including studies of atmospheric pressure and humidity. He kept extensive records of weather observations, which were some of the first systematic weather data. Color blindness. Dalton himself was colorblind, and he conducted early studies on the condition, which came to be known as Daltonism in his honor. Legacy. Advancement of chemistry. Dalton's atomic theory is regarded as one of the cornerstones of modern chemistry. It provided a framework for understanding chemical compounds and reactions at a molecular level. Influence on subsequent discoveries. His theory inspired further scientific inquiry into the nature of matter, leading to discoveries like J.J. Thomson's identification of the electron, Ernest Rutherford's model of the atomic nucleus, and the development of quantum mechanics. Recognition and later life. Scientific recognition. Dalton gained recognition for his contribution to chemistry during his lifetime. He received several honors, including membership in the Royal Society, and became a prominent figure in British science. Later years, Dalton continued his scientific research until his death in 1844. He suffered a series of strokes towards the end of his life, but remained engaged in his work, reflecting his dedication to science. In summary, John Dalton's formulation of the first modern atomic theory in 1803 was a major milestone in the history of chemistry and science as a whole. His work transformed the ancient idea of atoms into a specific framework that could explain chemical reactions, property of gases, and the composition of matter. Despite some inaccuracies, Dalton's atomic theory laid the foundation for the development of modern atomic physics and chemistry, shaping our understanding of the building blocks of the universe.
Kinds of stuff Professor Dave explains.
Dmitry Mendeleev creates the first periodic table of elements, 1869. Dmitry Mendeleev was a Russian chemist who is best known for creating the first widely recognized periodic table of elements in 1869. His work marked a pivotal moment in the development of chemistry, providing a systematic way to organize the known elements based on their properties. Chemistry in the 19th century. By the mid 19th century, many elements had been discovered and chemists were struggling to make sense of patterns and relationships between them. There was a growing recognition that some elements shared similar chemical properties, but there was no standardized system for organizing them. Attempts at classification. Several attempts had been made to classify elements before Mendeleev. Scientists like Johann Wolfgang, Dauber-Reiner, John Newlands, and Alexandra Emil Begoya Dushan-Kota had all tried to find patterns among them. Dauber-Reiner triads, 1829. Dauber-Reiner grouped elements into sets of three triads, based on similarities in chemical properties, noting that the atomic weight of the middle elements was roughly the average of the other two. Newland's Law of Octaves, 1864. John Newlands proposed arranging elements by increasing atomic weight, observing that every eighth element exhibited similar properties. However, this idea was met with skepticism and not widely accepted. Dushan-Kota, Telluric Helix, 1862. Dushan-Kota developed a helical arrangement of elements based on atomic weights, but his work failed to gain widespread recognition. Early life, 1834 to 1907. Dmitry Mendeleev was born in Tobolsk, Siberia. He studied chemistry in St. Petersburg and later worked as a professor. Mendeleev had a strong foundation in chemical research well as an interest in finding order in complex systems. Research on atomic weights. Mendeleev's interest in the classification of elements grew out of his work on determining atomic weights. He wanted to find a way to organize the known elements to better understand their chemical behavior. Organizing elements by atomic weight. In 1869, Mendeleev arranged the 63 known elements in order of increasing atomic weight. He noticed that similar properties recurred at regular intervals, leading to a periodic repetition of properties. Periodic law. Mendeleev formulated the periodic law, which states that when elements are arranged in order of increasing atomic weight, their chemical and physical properties show a periodic pattern. This law helped him construct the first version of the periodic table. Gaps and prediction. One of Mendeleev's most significant contributions was leaving gaps in his periodic table for elements that had not yet been discovered. He predicted the existence and properties of these missing elements, such as gallium, scandium, and germanium. Mendeleev's predictions were remarkably accurate, and the later discovery of these elements validated his table and solidified his reputation. Rearranging elements. Mendeleev sometimes broke the strict order of increasing atomic weights to place elements in groups with similar properties. For instance, he placed iodine after tellurium, despite iodine having a lower atomic weight, correctly recognizing that its chemical properties match the halogens. Groups and periods. Mendeleev's periodic table arranged elements in rows and columns according to their properties. Elements in the same column had similar chemical behavior, which highlighted patterns across different types of elements. Table structure. The original version of the table was much smaller than today's version, as many elements had not yet been discovered. It contained several gaps that Mendeleev confidently anticipated would be filled by future discoveries. Predictive power. The most revolutionary aspect of Mendeleev's periodic table was its predictive power. He correctly predicted the properties of several elements, including gallium, discovered in 1875. Gallium's properties closely match Mendeleev's predictions for aka aluminum. Scandium, discovered in 1879. Scandium also fits Mendeleev's predictions. Germanium, discovered in 1886. Germanium's properties match those Mendeleev had forecast. Validation of the periodic table. This successful prediction gave Mendeleev's periodic table significant credibility, convincing the scientific community of the utilities of his classification system. Foundation for modern chemistry. The periodic table provides a framework for understanding the relationships between elements and their compounds. It laid the groundwork for later discoveries, including the development of atomic theory, quantum mechanics, and chemical bonding theories. Moseley's contribution, 1913. In 1913, Henry Moseley refined the periodic law by showing that the properties of elements are better correlated with atomic number rather than atomic weight. This discovery led to a more accurate periodic table, resolving anomalies like those involving iodine and tellurium. Periodic table expansion. With the discovery of noble gases and synthetic elements, the periodic table expanded. It was restructured several times as new insights into atomic structure emerged, including the understanding of electron configurations. Modern periodic law. The modern version of the periodic law states the properties of elements are a periodic function of their atomic numbers, reflecting their electron configuration and corresponding chemical behaviors. Physical chemistry. Mendeleev made contribution to physical chemistry, including studies on the properties of gases and liquids. He formulated a version of the ideal gas law that included both temperature and pressure. Work on solutions. Mendeleev conducted research on solutions and contributed to understanding their properties, especially regarding alcohol and water mixtures. Petroleum industry in standardizations. Mendeleev also played a role in developing the Russian petroleum industry, and he worked on the standardization of various chemical substances, helping to advance the practical applications of chemistry. Reputation and honors. Mendeleev's work on the periodic table made him one of the most renowned chemists of his time. He received several honors, including being nominated for the Nobel Prize in Chemistry, though he never won it. Later life. Despite his groundbreaking work, Mendeleev faced some challenges. He fell out of favor with the Russian government due to his support for educational reforms and his sometimes controversial political views. He continued his scientific work until his death in 1907. Element 101. Mendelevium, in recognition of his contribution to chemistry. The synthetic element Mendelevium element number 101 was named in his honor in 1955. Periodic table as a tool. The periodic table remains one of the most important tools in science. It allows chemists to predict the behavior of elements, understand trends in reactivity, and explore the formation of compounds. It is a cornerstone of both chemistry education and advanced research. Influence on later discoveries. Mendeleev's work influenced future research on atomic structure, nuclear chemistry, and quantum mechanics. The periodic table's layout helped guide the discovery of new elements and further the understanding of atomic interactions. Symbol of scientific progress. The periodic table is often seen as a symbol of the power of human reasoning, representing how scientific inquiry can uncover the underlying order of nature. Gaps for future elements. Mendeleev's courage in leaving gaps for yet to be discovered elements showcases confidence in the periodic law's ability to predict new substances. Periodic trends. Mendeleev identified that properties such as valence, reactivity, and other chemical characteristics followed predictable trends as one moved across or down the table. These trends formed the basis of the table's organization. In summary, Dmitry Mendeleev's creation of the first periodic table of elements in 1869 was a milestone in the history of chemistry. His systematic arrangement of the elements, based on increasing atomic weight and recurring chemical properties, allowed him to predict the existence of yet to be discovered elements, demonstrating the power and potential of the periodic law. Mendeleev's work established the periodic table as an indispensable tool for understanding the natural world, providing a framework that continues to shape chemistry and science today.
Kinds of stuff Professor Dave explains.
J. Thomson, an English physicist, is best known for his discovery of the electron in 1897, which marked a major breakthrough in our understanding of atomic structure. His work fundamentally changed the way scientists viewed the atom and laid the groundwork for the development of modern atomic theory and quantum physics. 19th century atomic models. Before Thomson's discovery, the atom was generally thought to be indivisible and was often considered the smallest unit of matter, following John Dalton's atomic theory. Dalton's model described atoms as solid, indivisible particles, but it did not include any internal structure. Cathode ray studies. In the late 19th century, many scientists were experimenting with cathode ray tubes, glass tubes filled with the gas at low pressure with electrodes at each end. When a high voltage was applied across the electrodes, a mysterious beam known as a cathode ray was produced, raising questions about its nature. Early life, year 1856 to 1940. Joseph John Thomson, born in Manchester, England, was a gifted student who went on to study mathematics and experimental physics at Owens College, and later at the University of Cambridge. Appointment at Cambridge. Thomson became the director of the Cavendish Laboratory at Cambridge University in 1884, which was one of the leading centers for experimental physics. This position allowed him access to advanced experimental equipment and resources to investigate cathode rays. Investigating cathode rays. In the late 1890s, Thomson conducted a series of experiments with cathode rays tubes to determine the nature of these rays. There was debate among scientists about whether cathode rays were a type of electromagnetic wave or a stream of particles. Deflection by magnetic and electric fields. Thomson observed that cathode rays could be deflected by both electric and magnetic field. suggesting they had charge and mass. This reflection was not consistent with the behavior of light waves, but it was consistent with the behavior of particles. Measurement of charge to mass ratio. Thomson calculated the charge to mass ratio of these particles by applying electric and magnetic fields in opposition to one another and measuring the deflection. His results indicated that these particles were much smaller and lighter than atoms, about 1,800 the mass of a hydrogen atom, the lightest element known. Atoms as composite structures. Thomson's discovery shattered the idea of the atom as a solid, indivisible particle and revealed that atoms were made up of smaller components. This marked the beginning of our understanding of the subatomic structure of matter. Contribution to understanding electricity. The discovery of the electron helped explain electrical conductivity, as electrons were identified as the carriers of the electric current in metals. Proposing a new model of the atom, year 1904. Following his discovery, Thomson proposed a model of the atom known as the plum pudding model, sometimes called the raisin bread model. In this model, the atom was described as a positively charged sphere with negatively charged electrons embedded throughout, much like raisins in a pudding or seeds in a watermelon. Positive and negative charges. The atom was considered to be neutral overall, with the positive charge spread evenly throughout the atom and the negatively charged electrons embedded within it. Lack of nucleus. This model did not include the concept of a nucleus, which was introduced later by Ernest Rutherford in 1911. Rutherford's gold foil experiment, 1911. In 1911, Thomson's student Ernest Rutherford conducted their gold foil experiment, which revealed that the atom contains a dense, positively charged nucleus. This discovery disproved the plum pudding model and led to the development of the nuclear model of the atom. Limitations of Thomson's model. Thomson's model failed to explain certain atomic properties, such as the scattering of alpha particles observed by Rutherford, and it could not account for the discrete spectral lines of elements. Recognition and awards. J.J. Thomson's work was highly recognized, and he was awarded the Nobel Prize in Physics in 1906 for his discovery of the electron and his work on the conduction of electricity in gases. Mentoring the next generation. As the director of the Cavendish Laboratory, Thomson mentored many notable physicists, including Ernest Rutherford and Niels Bohr, who would go on to make major contributions to atomic theory. Discovery of isotopes, 1913. Thomson also conducted research on the positive rays produced in discharge tubes and discovered isotopes of certain elements which showed that atoms of the same element could have different masses. Electrons as fundamental particles. The discovery of the electron was a crucial step towards understanding the complexity of atom. It led to the realization that atoms have an internal structure consisting of a nucleus and electrons, which further led to the development of quantum mechanics. Development of atomic models. Thomson's discovery set the stage for subsequent atomic models, including Rutherford's nuclear model and Bohr's quantum model. It ultimately contributed to the understanding of atomic orbitals, quantum numbers, and the behavior of electrons in atoms. The start of quantum physics. The study of electrons and their properties was fundamental to the rise of quantum physics. Electrons' wave-particle duality, as described by later scientists like Louis de Broglie and Ernst Schrödinger, became a key aspect of quantum mechanics. Cathode rays and mass spectrometry. Thomson's work on cathode rays led to the development of mass spectrometry, an important tool in chemistry and physics. Thomson used his method to identify different isotopes of elements, which was critical to understanding atomic masses. The nature of electricity. Thomson's investigations contributed to understanding the nature of electricity, demonstrating that electric current in gases involves the flow of particles. This understanding was foundational for the later development of electronics in various electrical technologies. Nobel Prize in Physics, 1906.
J.J. Thomson was awarded the Nobel Prize in Physics for his work on the conduction of electricity in gases, which included the discovery of the electron. Title and honors. In recognition of his contributions, Thomson was knighted in 1908 and received numerous awards and honorary degrees. He also served as the Master of Trinity College, Cambridge from 1918 until his death. Later research and death. Thomson continued his research into atomic structure, isotopes, and the behavior of subatomic particles until his death in 1940. His son, George Paget Thomson, would also go on to win a Nobel Prize in Physics in 1937 for his work on electron diffraction, further cementing the Thomson's family legacy in the field of physics. Birth of subatomic physics. Thomson's discovery of the electron marked the beginning of subatomic physics and shifted the perception of the atom from an indivisible particle to a composite of smaller particles. Pioneering techniques. The experimental techniques of Thomson, developed to measure the properties of electrons, paved the way for further experiments in atomic and nuclear physics. Foundational role in quantum theory. The discovery of the electron also played a key role in the formulation of quantum theory. Understanding the behavior of electrons, including their energy levels and interaction, became central to the development of quantum mechanics, atomic theory, and ultimately to technologies like semiconductors and lasers. In summary, J.J. Thomson's discovery of the electron in 1897 fundamentally altered the understanding of atomic structure. By demonstrating that atoms are composed of smaller negatively charged particles, Thomson paved the way for the development of atomic physics and modern quantum theory. His work laid the foundation for future discoveries about the structure of atoms, the forces within them, and the quantum behavior of subatomic particles, establishing him as one of the pioneers of modern physics.
Kinds of stuff Professor Dave explains.
Ernest Rutherford proposed the nuclear model of the atom in 1911. Ernest Rutherford, a New Zealand-born physicist, is known as the father of nuclear physics in 1911. Rutherford proposed the nuclear model of the atom, which radically changed the understanding of atomic structure. This model introduced the concept of a dense, positively charged nucleus at the center of the atom, around which electrons orbit. Rutherford's experiment with alpha particles and gold foil play a pivotal role in shaping modern atomic theory. And number 1. Historical context. 19th century understanding of the atom. Prior to the Rutherford work, the prevailing model of the atom was J.J. Thomson plum pudding model in 1904, which described the atom as a uniform, positively charged sphere with negatively charged electrons embedded within. This model suggested that the positive charge was spread out evenly through the atom, resulting in no distinct nucleus. And number 2. Rutherford's early life and background. Early life in 1871 to 1937. Ernest Rutherford was born in Brightwater, New Zealand. He attended the University of New Zealand and later moved to England, where he studied at the combination laboratory at the Cambridge University under J.J. Thomson. Research on radioactivity. Rutherford's early work focuses on radioactivity, where he discovered and characterized two types of radiation, alpha and beta rays. Based on their penetrating power, he also worked with the periodic study to explain the concept of a radioactive to decay. Number 3. The Guilfoyle experiment in 1909 to 1911. Collaboration Hans Ginger and Ernest Marsden. Rutherford's most famous experiment, the Guilfoyle experiment, was conducted between 1909 and 1911 with the help of his student Hans Ginger and Ernest Marsden at the University of Manchester. They designed the experiment to study the behavior of alpha particles when they interacted with a matter. Setup of the experiment. In number 1, alpha particle source. The team used a radioactive source to emit alpha particles, which are positively charged and relatively heavy. Number 2. Gold foil. The alpha particles were directed at a very thin sheet of gold foil about 100 atoms thick. Number 3. Detection screen. A fluorescent screen created with a zinc sulfide was placed around the foil to detect the scattering of alpha particles. When an alpha particle struck the screen, a tiny flash of light was produced which could be observed with a microscope. And the result. In number 1, most particles pass straight through. The vast majority of alpha particles pass through the gold foil without deflection, which indicated that the atoms are mostly empty space. Number 2. Some particles deflection at large angles. A small fraction of alpha particles was reflected at significant angles, and a very few were even reflected directly back toward the source. This was a surprising and puzzling result that was inconsistent with the plum pudding model. Rutherford's conclusion. Nuclear model of the atom in 1911. Number 1. Rutherford concluded that the positive charge in the atom and most of its mass must be concentrated in a very small, dense region which we call the nucleus. Number 2. The rest of the atom was primarily empty space, allowing the most alpha particles to pass through foil without deflection. And number 3. The positively charged alpha particles were deflected when they came close to the dense, positively charged nucleus. Number 4. Key features of Rutherford's nuclear model. Central nucleus. In Rutherford's model, the atom consisted of a dense, positively charged nucleus at the center. The nucleus contained nearly all of the atom's mass. Electrons orbiting the nucleus. The electrons were true to move around the nucleus in an undefined manner, much like planets orbiting the sun. This model did not fully describe how the electrons were arranged, but it just suggested that they were located outside the nucleus. Empty space. Most of the volume of the atom was empty space, which allowed the alpha particles to pass through with a little to no deflection. Number 5. Impact on atomic theory. End of the Flan pudding model. Rutherford's nuclear model disproved J.J. Thomson's plum pudding model. The experimental results clearly show that the positive charge was not spread evenly through that the atom but was instead concentrated in a small region. Foundation for future models. Rutherford's nuclear model laid the foundation for Niels Bohr's atomic model in 1913. Bohr expanded upon Rutherford's work by proposing that electrons occupy specific energy levels or orbits around the nucleus, introducing the concept of quantized energy levels. Number 6. Challenges to Rutherford's model. Stability of the atom. One major issue with Rutherford's model was that it could not explain why electrons do not spiral into the nucleus. According to the classical physics, an electron moving in a circular orbit would emit radiation, lose energy, and eventually collapse into the nucleus, making the atom unstoppable. Development of quantum mechanics. The problem of atomic stability was eventually addressed by the development of quantum mechanics. Niels Bohr introduced the idea that electrons occupy discrete energy levels and do not radiate energy as long as they remain in a stable orbit, providing an explanation for atomic stability that the Rutherford's model lacked. Number 7. Rutherford's later contribution to nuclear physics. Discovery of the proton in 1917. Rutherford continued his research into nuclear physics, and in 1917 he discovered the proton by bombarding nitrogen gas with alpha particles, which result in the release of nitrogen nuclei. He demonstrated the hydrogen nucleus or proton was a fundamental building block of the atom nucleus. Nuclear transmutation. Rutherford's work on bombarding element and changing one element into another was an early form of a nuclear transmutation, paving the way for the later discovery of artificial nuclear reaction and the development of nuclear physics. The neutron in 1932. Rutherford's nuclear model predicted the presence of additional neutral particles within the nucleus to account for the mass that could not be explained by protons alone. His hypothesis was confirmed when James Chadwick, one of the Rutherford students, discovered the neutron in 1932. Number 8. Rutherford's legacy and influence. Mentoring future scientists. As a leader at the Cavendish Laboratory, Rutherford mentored several prominent scientists who would go on to make significant contributions to physics, including James Chadwick, who discovered the neutron, Niels Bohr, who developed the Bohr models of the atom, and Ernest Lawrence, inventor of the cyclotron. Nuclear physics pioneer. Rutherford is often called the father of nuclear physics due to his pioneering work on understanding the nucleus and radioactivity. His experiments laid the groundwork for the discovery of nuclear fission and later developments in nuclear energy and atomic weapons. Nobel Prize in Chemistry in 1908. Rutherford received the Nobel Prize in Chemistry in 1908 for his investigation into the disintegration of elements and the chemistry of radioactivity substances, although he is often remembered for his contribution to physics. This recognition was for his groundbreaking work in the field of chemistry. Element naming. In recognition of his contribution to science, element 104 was named Rutherfordium in his honor. Number 9. Significance and application of Rutherford's work. Revolutionizing the atom model. Rutherford's work completely changed the scientific community's view of the atom. The discovery of the nucleus led to a deeper understanding of atomic structure and eventually to the development of the quantum mechanical model of the atom, inspiring future research. The nuclear model of the atom inspired the further research into subatomic particles, atomic behavior, and the forces that hold the nucleus together. This ultimately led to the development of quantum theory and particle physics, two major areas of modern science. Nuclear reaction and fission. Rutherford's research on bombarding nuclei was an important precursor to the discovery of nuclear fission by Otto Hahn and Lise Meitner in 1938. This led to the development of both nuclear power and atomic weapons, highlighting both the beneficial and destructive potential nuclear science. Number 10. Key features of Rutherford's experiment and findings. Alpha particles and probes. Rutherford's use of alpha particles to probe atomic structure was a novel approach that allows for the identification of the dense and positively charged nucleus. Large deflection and backscattering. The observation that some alpha particles were deflected at large angles or even backscatter provide the key inside the atoms of a small, massive center contradicting the notion the atom were uniformly composed. In the summary, Ernest Rutherford's proposal of the nuclear model of the atom in 1911 marked a turning point in the understanding of atomic structure. His gold-foil experiment demonstrated that the atom have a dense, positively charged nucleus and mostly empty space. This discovery laid the foundation for the development of modern atomic theory, quantum mechanics, and nuclear physics. Rutherford's pioneering work not only altered the course of atomic science, but also the stage for the future research on the fundamental nature.
Kinds of stuff Professor Dave explains.
Niels Bohr develops the Bohr model of the atom. 1913. Niels Bohr, a Danish physicist, revolutionized atomic theory by developing the Bohr model of the atom in 1913. This model provided a quantum explanation of atomic structure, especially the arrangement of electrons and how they determine an atom's property by combining classical physics with early quantum ideas. Bohr was able to explain many of the inconsistencies of previous atomic models and shed light on the behavior of electrons. 1. Historical context. In an early atomic models, before Bohr's work, several atomic models had been proposed. First, Dalton's atomic theory in 1803. John Dalton viewed atoms as an indivisible solid spheres. Second, Thomson's plum pudding model, 1904. J.J. Thomson, who discovered the electron, proposed that atoms consist of negatively charged electrons embedded in a positively charged soup. Third, Rutherford's nuclear model, 1911. Ernest Rutherford's gold foil experiment revealed that atoms contain a dense, positively charged nucleus surrounded by empty space. However, Rutherford's model could not explain how electrons were arranged or why atoms were stable. In quantum concepts introduced by Max Planck and Albert Einstein, by the early 20th century, quantum mechanics had begun to emerge. Max Planck worked on blackbody radiation in 1900s, and Albert Einstein's photoelectric effect explanation in 1905 showed that energy comes in discrete packets or quanta. Bohr incorporated these concepts to address the shortcomings of Rutherford's model. 2. Niels Bohr's background and contributions. In early life, 1885 to 1962, Niels Bohr was born in Copenhagen, Denmark, and showed a strong aptitude for both physics and mathematics from a young age. He pursued his education at the University of Copenhagen. Postgraduate work with Rutherford. Bohr traveled to Manchester in 1912 to work with Ernest Rutherford. During this time, he became familiar with Rutherford's model of the atom, but recognized its limitations. Bohr was particularly interested in understanding the behavior of electrons and the observed stability of atoms. 3. Develop of the Bohr model, 1913. Inspiration from quantum theory. Bohr was inspired by Planck's idea that energy levels are quantized. He applied these ideas to the hydrogen atom to describe how electrons orbit the nucleus. The key features of the Bohr model. First, quantized energy levels. Bohr proposed that electrons exist in specific quantized energy level or orbits around the nucleus. Each orbit corresponded to a particular energy level, and electrons could not only exist at this fixed distance. Second, energy transitions and photon emission. Electrons could move between energy levels by absorbing or emitting a quantum of energy. When an electron moved from a higher energy level to a lower one, a photon of specific frequency was emitted. The energy of the photon was equal to the difference in energy between the two levels. Third, stability of electrons in orbits. According to Bohr's model, electrons in stable orbits do not emit radiation. Thus, explaining why atoms do not collapse, which was a major issue with Rutherford's model. Electrons could only radiate or absorb energy when transitioning between these defined orbits. Mathematical formulation. Bohr used quantum mechanics to determine the allowed orbits and energy levels. The model successfully described the spectral lines of hydrogen and accurately predicted their wavelengths using a Rydberg formula. 4. Bohr's explanation of atomic spectra. In hydrogen line spectrum, one of Bohr's most significant achievements was explaining the line spectrum of hydrogen. Scientists had observed that hydrogen emitted light as discrete wavelengths, which created a series of spectral lines known as the Balmer series. Bohr's model provided a theoretical basis for these lines by showing that they were caused by electrons transitioning between quantized energy levels. In spectral series, Bohr's theory extended to other spectral series, such as the Lyman series in the ultraviolet range and the Fashkin series in the infrared range. Each series corresponded to electrons dropping to a specific energy level. 5. Impact of Bohr's model. The validation of quantum concepts. Bohr's model provided experimental verification of quantum concepts, showing that energy is quantized. This was an important step toward the development of quantum mechanics. Explanation of atomic stability. By introducing quantized orbits, Bohr's model resolved the problem of atomic stability. Electrons could occupy stable orbits without emitting energy. Foundation for quantum mechanics. Bohr's work paved the way for further developments in quantum theory. The concept of quantized angular momentum and discrete energy levels became essential to the understanding of atomic and molecular structure. 6. Limitations of the Bohr model. Limited to hydrogen-like atoms. Bohr's model worked well for hydrogen and other single-electron systems, but it struggled to accurately describe multi-electron atoms. The complexity of electron interaction in larger atoms required a more sophisticated theory. Incompatibility with Heisenberg's uncertainty principle. Bohr's model suggested that electrons traveled in one well-defined orbits, which later conflicted with Werner's Heisenberg uncertainty principle in 1927, which states that it is impossible to know both the position and momentum of an electron with absolute certainty. Failure to explain spectral fine structure. The model did not account for the fine structure in spectral lines observed with higher resolution, which required additional quantum numbers and the concept of electron spin. 7. Transition to quantum mechanics. Wave-particle duality. Bohr's model was an important bridge between classical and quantum physics. However, the development of wave mechanics by Erwin Schrödinger and the concept of wave-particle duality of electrons by Louis de Broglie required an even more nuanced model of atomic structure. Quantum mechanical model of the atom. By the mid-1920s, quantum mechanics had emerged as the new framework for understanding atomic and subatomic phenomena. Schrödinger wave equation and probability densities replaced Bohr's idea of fixed orbits with electron orbitals, regions where electrons are more likely to be found. 8. Niels Bohr's complementarity principle. Complementarity, 1928. Bohr also formulated the concept of the complementarity, which stated that particles like electrons can exhibit both particle-like and wave-like properties depending on the experimental setup. This principle became a central tenet of the Copenhagen interpretation of quantum mechanics, emphasizing that different measurements can reveal complementary aspects of reality. Copenhagen interpretation. Bohr played a major role in the development of Copenhagen interpretation of quantum mechanics, which described the probabilistic nature of the quantum states that the role of observation in determining the state of quantum system. 9. Niels Bohr's later contributions and influence. Atomic structure and the periodic table. Bohr extended his ideas to explain the periodic table by using the concept of energy levels and electron shells. He described how arrangement of electrons in shells affect the chemical properties of the elements. Work on nuclear physics. In the 1930s, Bohr made significant contributions to nuclear physics. He proposed the liquid drop model of the nucleus, which helped explain the nuclear fission, and process later used in the development of nuclear energy and atomic bombs. Manhattan Project. During World War II, Bohr contributed to the Manhattan Project, the Allied effort to develop atomic bombs. Although Bohr was deeply concerned about the ethical implication of nuclear weapons, he worked with other scientists to understand nuclear reactions. Advocacy for peaceful use of nuclear energy. After the war, Bohr became an advocate for the peaceful use of the nuclear energy and international cooperation in atomic research. 10. Recognition and rewards. The Nobel Prize in Physics, 1922. Niels Bohr received the Nobel Prize in Physics in 1922 for his contributions to the understanding of atomic structure and radiation. The Institute of Theoretical Physics. In 1921, Bohr founded the Institute of Theoretical Physics in Copenhagen, which became a leading center for research in quantum mechanics. Many prominent physicists of the 20th century, such as Werner Heisenberg and Wolfgang Pauli, worked with Bohr there. 11. Significance of the Bohr model. In Quantum Leap, in understanding the atom, Bohr's model represented a major step forward in understanding the quantum nature of atomic structure. It introduced the idea that atomic behavior is governed by quantized rules, challenging classical views. Foundation for spectroscopy. The Bohr model laid the foundation for atomic spectroscopy. It allowed scientists to predict and understand the spectral lines emitted by elements, which is fundamental for identifying chemical elements both on Earth and in space. Legacy in education and research. The Bohr model remains a key teaching tool in chemistry and physics. Although it has been superseded by more sophisticated models, it provides an intuitive introduction to the quantum behavior of electrons. 12. Bohr's personal life and philosophy. Humanitarian efforts. Bohr was known for his humanitarian values during the World War II. He helped the numerous Jewish scientists escape from the Nazi persecution by inviting them to work at his institute. Bohr and Einstein debates. Bohr famously engaged in debates with Albert Einstein over the nature of quantum mechanics, while Einstein was skeptical of the probabilistic nature of quantum theory. Bohr defended the Copenhagen interpretation, emphasizing that quantum mechanics could accurately describe the behavior of subatomic particles. Bohr's influence on science policy. After the war, Bohr actively participated in discussions about nuclear disarmament and the responsible use of atomic energy. He advocated for openness and dialogue among nations concerning atomic research to ensure its peaceful application. In summary, Niels Bohr's development of the Bohr's model of the atom in 1913 was a groundbreaking achievement that combined classical and early quantum theories to explain atomic structure and spectral lines. His model introduced the idea of quantized energy levels for electrons, explaining the stability of atoms and the discrete nature of atomic spectra. Although it had been limitation and was later replaced by more advanced quantum models, the Bohr model played an essential role in shaping modern atomic theory and quantum mechanics. Bohr's broader contribution to the quantum theory and his leadership in the scientific community made him one of the most influential physicists of the 20th century.
Star Professor Dave explains.
James Chadwick discovers the neutron, 1932. James Chadwick, a British physicist, made a monumental contribution to atomic physics by discovering the neutron in 1932. This discovery completed the basic picture of atomic structure and had significant implications for both theoretical physics and practical applications such as nuclear energy and atomic weapons. 1. Historical context. Advances in atomic theory. By the early 1930s, the structure of the atom was partially understood. J.J. Thomson had discovered the electron in 1897, and Ernest Rutherford had proposed the nuclear model of the atom in 1911, which consisted of a dense, positively charged nucleus surrounded by negatively charged electrons. Protons, the positively charged particles in the nucleus, were already known, but there were a discrepancy between the atomic number and the atomic mass of many elements. This led to speculation that there must be another particle in the nucleus. Need for a neutral particle. The existence of an unknown neutral particle had been hypothesized by Rutherford in 1920 to account for the missing mass in the atomic nucleus. The proton-electron hypothesis could not explain the absurd atomic masses or the stability of nuclei, suggesting that a neutral particle must be present. 2. James Chadwick's early life and background. Early life, 1891 to 1974, James Chadwick was born in Cheshire, England. He attended the University of Manchester, where he worked under Ernest Rutherford. After completing his graduate studies, Chadwick followed Rutherford to the University of Cambridge, where he joined the Cavendish Laboratory. World War I and continued studies. Chadwick's studies were interrupted by World War I, during which he was interned in Germany. After the war, he returned to the Cavendish Laboratory, where he continued to work closely with Rutherford on nuclear physics and radioactive decay. 3. Experimental discovery of the neutron, 1932. Background to the experiment. Several experiments in the late 1920s and early 1930s provided hints of the neutron's existence. Physicists like Walter Bothe, Herbert Becker, Irene Curie, and Frederick Williot Curie observed unusual radiation when they bombarded elements like beryllium and alpha particles, but they misinterpreted it as gamma radiation. Chadwick's experiment. First, beryllium target and alpha particles. Chadwick used beryllium as a target and bombarded it with alpha particles from a polonium source. He noticed that the resulting radiation was capable of knocking protons out of the other materials, such as wax, which suggested it had significant amount of momentum but was not electrically charged. Second, detection of a neutral particle. Chadwick concluded that the radiation observed could not be explained by gamma rays. Instead, he proposed that it was due to previously known particle with no electric charge and a mass similar to the proton. He called this particle the neutron. Experimental proof. Chadwick measured the energy and momentum of the ejected protons and found the data were consistent with the presence of the neutral particle. This led him to confirm the neutron's existence. 4. Properties of the neutron. Neutral charge. The neutron has no electric charge, which is why it had remained undetected for so long. Its neurality allows it to pass through atomic electrons cloud and other charges without being deflected, making it difficult to detect with conventional methods. Mass. The neutron's mass is slightly greater than that of a proton, approximately 1.675 times 10 squared negative 27 kilogram. This mass accounts for the difference between an atom's atomic mass and its atomic number. Role in the nucleus. Neutrons along with the protons make up the atomic nucleus. Neutrons help stabilize the nucleus by offsetting the repulsive forces between positively charged protons. 5. Impact of Chadwick's discovery. Completion of the atomic model. Chadwick's discovery of the neutron was crucial for completing the basic model of the atom and explained why atomic nuclei were heavier than could be accounted for by protons alone. Advancement of nuclear physics. First, nuclear reactions. The neutron's discovery opened new avenues for nuclear research, as neutrons, being neutral, could penetrate nuclei without being repelled by electric charge. This made them ideal projectiles for initiating nuclear reaction. Second, nuclear fission and atomic bombs. Chadwick's discovery directly led to the development of the nuclear fission. In 1938, Otto Hahn and Lise Meitner discovered that bombarding uranium with neutrons caused the nucleus to split, releasing a tremendous amount of energy. This process of nuclear fission eventually became the basis for both nuclear power and atomic bombs. Chadwick himself played a role in the Manhattan Project, which developed the first atomic bombs during World War II. Newton proton model of the nucleus. With the discovery of the neutron, physicists could now explain the makeup of the atomic nucleus using only protons and neutrons. This model provided a better understanding of isotopes atoms of the same elements with different numbers of neutrons and explained the stability of different atomic nuclei. 6. Neutron's role in nuclear theory and quantum mechanics. Nuclear forces. The discovery of the neutron helped physicists understand the nature of the strong nuclear force, the force that holds protons and neutrons together in the nucleus. The role of neutrons in stabilizing the nucleus was fundamental to understanding why certain nuclei are stable and others are not. Isotopes and atomic mass. Neutrons explained the existence of isotopes, which are atoms of the same element that have the same number of protons but different numbers of neutrons. Isotopes have similar chemical properties but different atomic masses. This was crucial for explaining variation of atomic mass that could not be accounted by protons alone. Neutron activation analysis. The neutron's role in including nuclear reaction also led to the development of analytical techniques like neutron activation analysis, which is used to determine the composition of materials. 7. James Chadwick's later work and legacy. World War II and the Manhattan Project. During World War II, Chadwick played a significant role in the Manhattan Project, the Allied effort to develop atomic weapons. As a leading figure in British nuclear research, Chadwick worked closely with American scientists and provided crucial expertise on the behavior of neutrons and nuclear reactions. Nobel Prize in Physics, 1935. In recognition of his discovery of the neutron, James Chadwick was awarded the Nobel Prize in Physics in 1935. His work was instrumental in shaping the development of the nuclear physics and advancing the understanding of atomic structure. Knighthood and later career. Chadwick was knighted in 1945 for his contribution to science. After the war, he continued to contribute to the field of nuclear physics and played a role in shaping post-war nuclear policy. He became the master of Gonville and Caius College at Cambridge and was involved in the efforts to ensure the peaceful end use of atomic energy. 8. Significance of Chadwick's discovery. Paving the way for nuclear technology, the discovery of the neutron was a key factor in the development of nuclear reactors and nuclear weapons. Neutrons are essential for maintaining a chain reaction in both power reactor and nuclear bombs. Fundamental research in particle physics. Chadwick's discovery influenced subsequent research in particle physics. It helped in the classification of subatomic particles and provided a deeper understanding of the fundamental constituents of matter. Neutron scattering and research. The discovery led to the development of neutron scattering techniques, which have become essential tools in physics, chemistry, biology, and material science. Neutron scattering is used to investigate the atomic structure and properties of materials. 9. Challenges and difficulties in discovering the neutrons. Indirect detection. One of the main challenges in discovering the neutron was that it had no electric charge, making it difficult to detect using traditional methods that relied on ionizing or deflection in electromagnetic fields. Chadwick's clever experimental design, which involved observing the effects of the neutron collision on the nuclei, was key to confirming its existence. Misinterpretation of previous experiments. The radiation produced by beryllium and alpha particles had been misinterpreted by other scientists as high-energy gamma rays. Chadwick's insight that this radiation was in fact a new type of neutral particle demonstrated his experimental skill and deep understanding of nuclear processes. 10. Theoretical frameworks in nuclear physics. Nuclear models. Chadwick's discovery led to the development of various nuclear models, including the liquid drop model and the shell model, which describe the structure and behavior of atomic nuclei in terms of neutrons and protons. Advancement in quantum field theory. The incorporation of neutrons into the broader framework of the quantum field theory enabled physicists to explore new theories and models describing the behavior of subatomic particles. In summary, James Chadwick's discovery of the neutron in 1932 marked a pivotal moment in atomic physics, providing a complete understanding of atomic structure and enabling further developments in nuclear physics and technology. His works laid the groundwork for advancement in nuclear energy, medical imaging, and particle physics, and his legacy continues to influence scientific research today.